was like $500.
Yeah.
Oh, because I got the
Go to the what did I miss? Unit 4. Grab the notes and the
yeah, the cool.
Those are my favorite.
Okay, here we go, everybody. Give me your attention this way. Put all your distractions away. Here we go. All right, so last time, the two big things we talked about were we learned about the difference between a chemical and physical reaction, and what were those, and then we learned how to balance a chemical equation. We ended last time by looking at this example one, and this is what we're going to pick up. So we have this sentence here that describes a process that's happening. Now, as we're going through today's lesson, and I'll do some different things to help this, but I can only encourage it, like you're the one who has to make your brain think in these ways. As always, I encourage you to think about all three sides of our triangle. Okay, think about what do we see with our eyes with what it's saying, what is going on at the molecular level, and then symbolically, in our case, a lot of times it's going to be like the balanced equation and the math, right? See how all three sides connect, and chemistry makes sense. If you focus on just one side, and I'll say the one most students do is the symbolic, they focus so much on the chemical symbols and the numbers, but they don't really even understand what's happening. And that can make every problem feel different and harder. But if you see the whole picture, every problem we do today as well as next time should feel like, oh, it's pretty much the same thing again. Because in the big picture, it's all the same idea of what's happening. Okay? So I'll kind of do some things, we'll do some demonstrations to kind of help you give that vision. But I would encourage you to think about that, once again, in different ways. So in this case, symbolically we started by writing the balanced equation, okay, where the balanced equation is just based on what's happening and what's being made. Okay, so our balanced equation we came up with was, we had nitrogen, which is N2, reacting with H2 to make NH3, which is ammonia. Once again, the problem would have given you the formula for ammonia. You don't have to have that memorized or anything. But let's talk about really quick. So if you want to kind of make a match, so nitrogen is N. Can someone by raise a hand remind us why is it N2 and not just N? Yeah. Say it one more time. Yes, because we have those 7 diatomic molecules. Now, they're not actually all gases. One of them is a liquid, but most of them are gases. Right? You have this little chart. Right? Those ones always exist as a 2. They cannot exist in nature individually. So every time you take a breath, you're breathing in N2O2. You're not breathing in single N's. Other things not on that chart could just be themselves, like sodium. Pure sodium is just Na. Now keep in mind the 2 is only a requirement when it's by itself as a pure substance. Once they're in a compound, the compound is just whatever the compound is. But don't get carried away. Some people start adding like 2's into compounds because they're like, oh, it's diatomic. Right? Only applies when it's alone. Okay? We then had to balance it because there are 3 of these on this side, so that doesn't make sense. So this is what we learned last time, right? So I put a 3 there and a 2 there because now you have the same amount on both sides. Sorry for those that were gone last time. If you haven't watched the video, that was just like showing you the answer. But there's like a process of like how to get there. Okay? Now, where the 3 and 3 up in the word problem come into play is that's the actual experiment. As a chemist, you can pour together whatever you want. I mean, obviously, like, you might be wasting money if you pour a bunch together, but, like, you can do whatever you want from your cupboard. And so this picture right here, that's where the 3 and 3 match up. It's not the balanced equation. But what the balanced equation does is it dictates how the reaction happens. So in this problem, we're going to draw an after picture after the reaction occurs. So from our balanced equation, let me get this front light here. Our balanced equation says for every 1 nitrogen molecule, it needs to react with 3 hydrogen molecules. So the way I like to solve these out is by matching them up in the ratio. So this one, notice, is our nitrogen. Black are the hydrogen. So I'm going to pair up 1, 2, 3. For every 1 of these, I need 3 of those because that's what the balanced equation told me. 1 to 3. Now it's going to make 2 NH3s when that happens. So in my after box, I'm going to draw 2 molecules of NH3. So N is our open circle, H's are closed circles, so to draw to NH3, I draw one N with 3 H's. And I have 2 of them that got made based on what I poured together. So as a chemist, you get to pick what's in the starting box. You don't pick what's in the end box. The end box is just what gets created based on what you chose to pour together. Now, there are things in that starting box that didn't react. So we need to show them in the after, because things can't just get destroyed or disappear. So over here, we should also have those 2 random molecules of nitrogen that had nothing to react with. In terms of vocabulary, we would call our nitrogen our excess. Because there was left over it after the reaction happened, right? There in the beginning, there in the end. Okay? The limiting reactant is the one that we ran out of, and so the reaction stopped, and so that would be our hydrogen. Questions on these vocab words of limiting versus excess? Okay, don't say anything out loud. I want you to think in your head, and then I'll have you share the table. Okay? Is it possible to have more than one excess? Don't say it out loud. Is it possible to have more than one in excess? Okay, turn to your table and tell them what you think. Yes, no, why? Go.
Yes.
Yes.
Yep.
Because there are certain things that won't react with each other.
And you can have an ending molecule with like 20 billion, like 20 atoms.
Yeah.
And there's going to be some excess of different things. Hopefully I never see that on a test. But it could happen.
Yeah, hopefully that's not on the AP exam.
That would suck.
If it was,
Then we would figure it out.
yes.
And it's only one question. So it's not that bad.
Okay, raise a hand. Let's hear a thought. Is it possible to have more than one excess? What do we think? All right, everyone close your mouths. Zachary has the floor. Tell us, Zachary, what do you think? Why?
Because you have like 3 components to the reaction, and only one runs out, you can have 2 of the components still around.
Good, so one option is you can have a reaction where you have 3 reactants, right? Reactions don't have to be just 2 things combining, they could be up to 3 things combining, and then definitely you can have more than one excess. Good, how was my pitch that? Someone else have a different thought or about that? Other Zach.
So I was saying, like, if you need 4 of these, 4 of one of these with 3 of one of these to make a new molecule, then if you left with only 2 of these and then like 1 of these, then you can't put those together. You have 2 different.
So like in this one, if I added in another H, could I make more product? Not yet, right? Because I need a 3-to-1 ratio. And so, yep, you can have more than one in excess. In a sense, the limiting can also sometimes be the excess, because it's just about which one ran out of first, but it may ran out of in terms of the ratio. Okay? This is what your homework 4.3 is all about, is given these pictures, drawing me the end product of what will still be in. Now, once again, the biggest mistake and confusion I saw students make, and I added some extra things onto that homework to kind of remind you, but number one is they forgot about things that were diatomic, and so when they drew their before picture, right, for their balanced equation, they didn't make them diatomic if they are diatomic. But then the second thing is mixing up the sentence with the equation, and they would say, oh, 3 and 3, and so they put 3 and 3 as your balanced equation, which is like never going to work out to be balanced. So keep that in mind of the difference between, once again, I kind of made the analogy of this is your recipe, right? The recipe is a set thing based on the ingredients. The box is your cupboard. You can have whatever you want in your cupboard, right? Yeah, Christina. No, so we'll also learn how to do that today as well. I meant to put that up there as well as do the backside. So, okay, questions on this? Okay, with that, let's go to now a word problem, but the same concept of what's going on. So when I look at this balanced equation, so we're still using the same one, so write this equation again under this problem, just to remind you, like, we're still looking at the same equation. Okay? These numbers that tell us the ratio actually tell you two things as the same thing. One, they are a molecule-to-molecule relationship. For every one molecule of this, I need 3 molecules of this, and it will make 2 molecules of that. These numbers also tell you the mole relationship. Moles and molecules are proportionate. So this also tells me for 1 mole of this, I need 3 moles of this, and it will make 2 moles of this. And the mole is what bridges our gap between what I can't see to what I can. Because I can't see a single atom, but I can see a mole of atoms. That's big enough for me to see. And so keep in mind it's the same, but this is known, if you want to label it, is also known as the mole ratio. So in this problem here, it says if I want to create 6 moles of NH3, how many moles of N2 and H2 would I need? Okay, so in a sense, they want to say, well, I now want 6 of this. So to change it, once again, the ratio must be maintained. It has to stay balanced. So how much of this would I need? 9. Because to go from here to here, it changed by 3. To go here to here, it must also, like in math, what you do to one side of the equation, you have to do to the other. Hope I can do that. So I would need 3 moles of nitrogen and 9 moles of hydrogen in order to make 6 moles of NH3. Now, if I were to do this reaction, this is what you would call the perfect stoichiometric ratio, because you don't have any excess. You don't have any leftover. It's the perfect ratio between them, which is like the most cost-efficient way to do a reaction, because then you don't have just leftover stuff. But sometimes some things in excess are pretty easy to get, right? Like nitrogen, there's like a lot of it in the air, so it's not, normally there's always one in excess. But Emily, did you have a question?
No, so how come not all of that have any access, but the other one is good?
So in the case of the other one, the thing they started with is they started with 3 of these and 3 of those. So the amounts they started with don't match the ratio. But in a sense, if you simplify 3 to 9, it turns to 1 and 3. So if the ratio matches what it should be, you don't have excess. But if it's off in any way, so like hypothetically you just change this, you're now going to have something in excess, because 4 to 9 doesn't reduce down to 1 to 3. Does that make sense? Yeah, good question. Any other questions on that? Now, this one's easier to see mathematically because 2 to 6, right, it's easy to see that transition. Let's look at a problem where it's not as clean of a number and we start dealing with decimals. So this one says if I have 0.32 moles of nitrogen and excess hydrogen, how much NH3 can be made? So same idea, but it's not quite as clean in terms of the change. So I erased our equation here. Okay? Now, before we solve the problem, I want to point out something. What's significant about them saying that we have excess hydrogen? Is that needed in a problem? Does that help us? Why is it there? Any thoughts? Yeah, Kenzie.
Is it because you don't have to balance it?
Yeah, it means we have plenty of it, so we don't have to focus on how much of that was there. Because otherwise, that's going to control how much of this can be made. So in a sense, we don't do anything with it, but if you don't know something's in excess, then you almost have to do 2 problems to know which one's going to run out first. Okay? All right, so in this problem, we're going to take what we know first. Now, in today's lesson, I'm going to be using different colored markers very strategically. So I would encourage you to grab some highlighters as well and add it to your notes to help you kind of see how this process fits together. Okay? You don't have to match your colors with mine, by the way. I mean, you can if you want to, but Just if two of my colors are matching, make sure yours are matching as well. That's the key part. Okay? So we're starting with 0.32 moles of N2. So start with what you know. Now the idea is we want to get to moles of NH3. So we're going to be doing lots of conversions today, similar to what we've done before with a little bit of twist, but still the idea of conversion. So when I'm converting, whatever unit is here should be the unit on the bottom. So that's where my colors are going to match. And I want to correlate it or connect it to moles of NH3. So those are the same because in a sense I want to convert out of this into that. Now anytime you have a fraction like this, right, a conversion factor, it is independent of the problem. It has nothing to do with this number. It's just what numbers correlate those two units together. Just like if it was inches over feet, right, it's 12 to 1. So how do I connect moles of nitrogen to moles of ammonia? Jack? The balanced equation, which is why we had to learn how to balance first. So the mole to mole relationship is always linked through the balanced equation. Have a smiley face, Jack. So in our case, it's 2 to 1. Because when there's nothing on the line, there's a 1 there, right? So for every one of these, it's going to make 2 of those. So that's where the 2 to 1 came from. Yeah, Bryson.
Sort of along those ideas, how I saw it was sort of obviously like a ratio. How I saw that since there's 1 and 2, and there has to be 2 NH3. So then like if there's like 2 N2s, then there's 4 NH3. So then I saw that there's 0.32 moles of N2, so then there has to be double that with the NH3.
And that's perfect. That's exactly what this fraction is showing us, right? It's showing us that the relationship between them is a 2 to 1, right? And so in a sense, our answer will be just doubled of 0.64 moles of NH3 is how much I'll be able to create. Right, so I just did 0.32 times by 2, give us there. Questions so far? This idea of our mole to mole relationship. Before we expound it slightly. Okay, turn your page over and let's take a look at this map here. All right. Okay, so this right here is what I call our stoichiometry map. Stoichiometry is a fancy word in chemistry that can make you sound really smart because most people think you're making up a word. It is a real word, but it's really specific to chemistry, so outside of it, people don't know what that is. But stoichiometry is just the process of converting units. Really doing like inches to feet is somewhat similar to what we do in stoichiometry. The difference is stoichiometry is just specific to chemical reactions and what's happening. Okay? So what we're going to be doing is on this map, we've actually already seen the left side before. Right? I've shown you actually this in a previous unit when we learned how to do those conversions. So let's go ahead and remind ourselves what the relationship is between these two. So for example, if I'm given grams, so let's say a problem says, hey, I have 2 grams of water. How many moles of water is it? In general, what connects grams to moles? Molar mass, yep. So add that on here. Now we're going to use the map as we solve these different problems, and I would encourage you, as you do this, use the map as much as you need. Eventually, we do have to do it without it, but I'm a firm believer if you just do something enough, you won't need it. But if you're getting stuck, this I found it's been very helpful for students. So if you're getting stuck, use it, and then eventually you won't need it anymore. Okay, so molar mass, Reminder, we find that on the periodic table, right? We add up how much it is. Okay? All right, particles to moles. What connects that relationship? Good. This is Avogadro, 6.02 times 10 to the 23rd. That number's on your formula sheet, by the way, so you don't have to have it memorized if you ever forget it. Avogadro's number, which is the value of a mole, right? 1 mole equals that many particles, right? If I have a mole of markers, it means I have 6.02 times 10 to the 23rd markers. So, okay, this one we talked about. We haven't used it in a conversion, but the connection between liters of solution and moles. Does anyone know what moles over liters equals?
Molarity.
Good job. Yep. So this is molarity. So molarity helps you convert from solution to moles. And then this one we've also used, not a ton, but we addressed it, when did we learn it? Oh, also in Unit 3 with our gas law, it's like a constant. It's 22.4 liter per mole. So it's just a constant value that if you have 1 mole of gas, it's always going to occupy 22.4 liters at standard temperature and pressure. So 1 mole of gas, a balloon will always be this size if you have 1 mole inside of it. So, okay, now this one we just learned about. What connects moles to moles? The mole ratio in the balanced equation. Yep. All right, so the balanced equation, that mole ratio is what allows you to bridge the gap between the given and the unknown. So this is what's changing in our conversions, is really just this middle piece. Before, all the problems, and you've had a conversion almost on every test we've taken, because I've tried to keep it somewhat fresh of, hey, if I have this many grams, how many moles is it? Or if I have this many moles, how many particles is it, right? We're going to do the same thing, but the difference is now the substance is changing. We're going to start with hydrogen, but end with water. Right, because we're going to go through an actual chemical process, a chemical change is going to happen. Now, you can fill it in, because if you notice the right side, what do you notice about the right side? It's the same thing, right? Because the relationships haven't changed once you cross that mole bridge, okay? Now, key thing once again here is moles are the center of the map. Moles are what connect what we can see. I can see liters of gas. I can see a gram. I can't really see particles, but I can see a liter of solution. Mole is what connects it to something else. So we have a saying in here that when in doubt, mole it out. Because you always go to mole before you go to anything else. So if you're ever stuck in a problem of like, where do I go? Go to moles. Because moles is always going to be the first step. Okay? All right, questions on our math before we try it with a problem? Okay, our problem says here, if 0.5 grams of calcium carbide, which is CaC2, are put into our first bottle with water, how many grams of acetylene, which is C2H2, will be made? Okay, now as I read problems, once again, my recommendation in terms of like kind of annotating it as I read is I underline given numbers, right? So that as I kind of go back and through, I like pull those out, and then I circle what is the unit I'm trying to find. Now the key thing here is you're going to want to not just circle the unit, but the substance. Grams of acetylene. So I circle what I'm trying to find, I underline where I'm starting, or what I know. Now before we solve this, let's bring this problem to life. What is this? Can someone rephrase? What is this asking? Like, paint a picture of a chemical reaction. What are we trying to do in this problem? For a smiley face, anyone reword it for us? Yeah, go ahead, Agla. We're trying to find the mass of what? Yeah, the C2H2. So I have some calcium carbide right here, right? Okay, so I have some CaC2. How much am I going to measure out?
0.5 grams.
I'm going to measure out 0.5 grams. What am I going to do with it?
Light it on fire.
In water.
I don't see any fire up there. I'm going to put it in water, right? Okay, now, is water important to this reaction?
Yes.
Yeah, it wouldn't happen without water. Why are we not focusing on water though in our problem? Yeah, we're saying we got plenty of it, right? Like it's not gonna run out, that's not our problem. Okay, we're gonna have plenty of it. Okay, what is it we're trying to find about after I drop this into water? What are we trying to find?
How much gas will be made?
Yeah, how much of this can I make? Right? Now what about this guy? Is he there? Is it excess?
Yes. Yeah.
No.
For this problem.
How would you label that? CA. We just don't care. That's why we label it. It's kind of true. It's another product being made, and in this problem, we're not focused on it, right? So it's not excess because it's not like leftovers. It's being made, but in this problem, we're not focused on it. So with stoichiometry, I want you to notice something here, and then we'll walk through it. Okay? In stoichiometry, in our case, we're comparing this to product. So reactant to product, which is a common way to look at it. But the question could also ask this to this. Maybe we want to know what is the perfect amount of water to use. So the question could say, if I have 0.5 grams of calcium carbide, how much water should I react it with? So you can compare this to this. You could compare product to product. Of saying, hey, if this much was made, how much of that was made? So you can compare any two things across the arrow, same side of arrow, when you're doing a stoichiometric relationship, because it's all just about how they're all connected. In general, there's normally going to be certain things you kind of just ignore because they're not part of it. Either they're an excess or they're just another product we're not focused on. Okay? All right, let's go to our map here and see how this is going to play out. Okay? So on our problem, it gave us a gram value. So this is my starting location. What's my ending location I'm trying to get to? Grams of something else. When you use the map, you're always going to go from the left, because you're given something, to the unknown. So in our case, it's going to take 1, 2, 3 steps to get there. Okay, so it's going to take 3 steps to go from what we know to what we don't know. There's no airplane. You can't just fly. You got to travel the roads. Okay? All right, so start with what's given. So 0.5 grams of CaC2. So write that down, everybody, as your starting point. Now, take it one step at a time. The first step is I got to go from grams of this substance to moles of this substance. Okay, so I set up this is my first step. The unit on the bottom should be the place you're leaving on your map. So I'm leaving grams of CaC2. The top of the fraction should be where you're going. I'm going to moles of the same thing. So I'm going to change color because I'm changing cities. Okay, so mole CaC2. Once again, notice the correlation. Once again, the bottom is where I'm leaving and should match where you were. The top is where I'm going. Now, I prefer to write out my whole map and then come back for the ratios. For me, it just helps my brain go all the way through the process. Okay, so I'm going to keep going here. Okay, so we've traveled from here to here. So I want to leave moles, so I'm going to put that on the bottom. And I want to go to, where are we headed? Moles of our unknown substance. So mole of C2H2. Okay. All right. Next step. Leaving mole of C2H2. going to grams C2H2. What is the only color that doesn't have a match in my map, right? So the pink is the only one, right, that doesn't have a match. That's because it's what I want to find. So it shouldn't. So the thing that doesn't have a match should be the thing you circled in your problem. If you didn't, then you set up something wrong. Okay, questions on our road setup here. Do we see how like this correlates to the steps? Okay, let's plug in our numbers. So each of these, once again, is independent of the others. Okay, don't like carry things through or carry something over. It's just what makes this equivalent. You should be able to change it into a sentence. Just like I can say 12 inches is 1 foot. How many moles is how many grams for calcium carbide? How do I find that? The molar mass. So we go to the periodic table, we add up calcium and 2 carbons, or I look on my chemical bottle because they show it on here. So it's 64.10. But generally you'd find this, right, from the periodic table. Because for every 1 calcium carbide, it weighs 64.10 grams. Because 1 calcium plus 2 carbons, if you want to write that, so calcium, here's your little thing, calcium is like 40.08, carbon is 12.01, times by 2, add that together, and that's how you get your 64. Questions on that? Just because the 2 right there. Yeah, good catch. Any other questions? Okay, this one, once again, ignore everything else. Just compare the 2 in the fraction. Moles of this to moles of that. How do I compare mole and mole? The balanced equation, right? How are they connected? So for every, so here's calcium carbide. There's no number in front, which means there's just one of those, and it makes one of these. So it's a 1-to-1 relationship. Questions on that? So you go to the balanced equation and just find that chemical. So C2H2, there's only 1. But like, so just to give you an example, if it was like water, then it would have been 2 and 1. Now with this and what Ian points out, I want to emphasize something here, everybody. All right, there's too much side talking going on. Okay, this is, I'm teaching, you're listening. If you think you know how to do it, I'm very happy for you. But I also care about all the other students in here and I want to help them learn. So you shouldn't be talking right now. Okay, even if you're like, I feel like I'm pro, then good for you, but close your mouth. Okay? With this step right here, okay, I totally understand mathematically this means nothing. Right? Mathematically, 1/1 is no change. But chemically speaking, that mole-to-mole relationship is everything. Right? The everything of understanding how those 2 are connected. You can't skip that relationship. Most of the time it's not going to be 1-to-1. It just happens to be this time. So, okay, final connection is mole to gram again. So, same thing before, but now it's the molar mass of C2H2. So add that up. It ends up being, I think, like 26.04 if I round it. So there's that many grams in every one. Once again, the unit should guide the numbers. Okay, another common thing that I see students do is like putting the 26 on the bottom. But if you read the units, it doesn't make sense because it's not 1 gram is 26 moles, right? It's 26 grams is 1 mole. Make it make sense, and all these problems can change but feel the same. Like I can literally ask you a million different stoichiometry problems, but if you see the big picture of it, they'll all feel the same. Okay? Now, typing this into your calculator, Here's how I would choose to type it in, because I don't want to type in all these fractions. That just feels like more work than that's necessary. So you got to start at the beginning. So in your calculator, put 0.5. Coming to the first fraction, if it's a 1, you can ignore it. If it's on the bottom, divide it. So I'm going to do 0.5 divided by 64.10. Another 1 and 1, so I'm going to ignore those. This is on the top of the fraction, so I'm going to times it. And then that will be your answer. So I think that's way faster than typing in 3 sets of fractions. So just ignore the ones, divide the bottom, times the top. Try typing that in for me, everybody, just to make sure you don't get it wrong that way. You should get 0.2 grams of C2H2 as your answer. Yeah.
Can I go on your calculator again?
Any questions on the setup or the numbers or anything along those lines? Okay, all right, try number 2 with your table buddy for a smiley face. Ready, go. So try number 2 on your notes, and then we'll check it. For smiley face. Here's what calcium carbide looks like. So this is 0.5 grams, this is 5 grams. Here's what our calcium carbide looks like. Yeah, looks like quite dangerous.
What did you guys get?
2 grams.
I got 2.0.
Yeah, but the sig figs make it.
Oh yeah, I see things.
Well, they get 2.0.
Yep, I got that too.
2.0.
Wait, did we ever learn how to do this?
Not yet.
Not yet.
Not yet.
Said we would learn. It's almost 50.
But I'm really excited.
swim?
So I got 3 bonus events, but I only picked 2. I did 200 IM and 100 fly.
Dang, that's
And then
nice.
The 200 fly.
I have to swim 6 events and 2 relays.
Oh wow.
And I have the 2 IM and the 4 IM on the same day.
That's gonna be so fun.
It's a lot of IM, but I'll be fine. Oh, wait, maybe it's only 5 events. That's
Only 5.
I think.
in 3 days. But the 200 fly is on the very last day.
200 fly is the very last day.
Yeah.
And it's very likable that I'll make it a finals just because nobody does.
Because it's the 200 fly, yeah. I'll make finals too. I'll make finals in the 4 IM. So maybe.
Yeah. Nobody wants to do this.
Because there's not even enough people to like have a full not finals.
Yeah.
Oh, in the 200 fly, I could be like top 16.
That would be really fun.
Yeah.
Ready? Does everyone have an answer?
Maybe. We'll see.
You could get a medal. You could probably get 8th place.
I could try.
You could be top
If
8.
enough people don't swim it, then.
That's what I'm hoping, that not enough people swim it, and then
Right now, I think 15, 16, I'm ranked like 3rd.
3rd. And then 200 fly.
And 15, 16, and 4th in the 100 fly. But there's also 17, 18.
Okay. So if you had an answer of 2 grams, you can have a smiley face. You're correct. Now, if you chose to set this up the same way we did number 1, that's totally fine, and obviously it gets you the right answer if you set it up correctly. But this is, once again, kind of as an example of, once again, reading a question and taking a big picture perspective of what is it saying. How is this one and number 1 similar? Go ahead, Porter.
You're trying to find the same thing.
Yeah, the product is the same thing, right? The thing we're focused on finding is still C2H2. What's changed, Porter?
The amount of this stuff provided.
Yeah, just how much I started with. And how much more did I do on number 2 than number 1?
Less.
10 times as much. So the answer should be 10 times as much. So you
Oh.
technically don't even have to set up the whole thing. Now, obviously I'm not saying like AP questions, but this is, once again, don't get so caught up in just like reading a question and not paying attention to like, what is it actually saying? Okay? All right, so we're gonna do both of these reactions now to see the difference in what it does. Now we obviously know from our stoichiometry which one's gonna make more acetylene.
5 grams.
5 grams, right? 5 grams is gonna make 10 times as much acetylene. Now, once again, there's a difference, and we'll get more into this next time, but there's a difference between what math says should happen and what actually happens. So we have something known as the theoretical and the actual yield. Theoretical yield is that answer on your paper. Because math is perfect, nothing gets spilled, nothing gets lost, nothing gets broken in math, and so everything goes perfect, I should be able to make that many grams. In actuality, I might not get that, because maybe I don't measure out my 5 correctly, maybe I spill some when I'm transferring it over, maybe my equipment is off, and so it may not line up. Most of the time it won't. Similar in cooking, right, where a recipe says you can make 2 dozen cookies, but you actually making 2 dozen cookies is dependent upon size of your cookies, how much cookie dough you eat, right, 'cause that's how I make cookies. So, but similar idea, okay? All right, so let's do 0.5 grams. Now, to see our acetylene, we're gonna do a second reaction. Because acetylene's a gas, it's clear, so we really can't see it. Like, I could trap it in a balloon, but like, it's only 0.2 grams, so it probably wouldn't even blow up the balloon. So gases are like hard to like quantify. So what I'm gonna do is I'm gonna do a second reaction with the acetylene. So if you look at number 3 here, so number 3 is acetylene gas, so the thing we're making is explosive with oxygen, okay? So I'm gonna do a second reaction where after the acetylene gets made, I'm gonna ignite it. Are we at our time, Gavin? Or yeah. Okay, let me do this and then we'll pass back our test. Thank you for the reminder though. Okay, and based off the explosion, that should help us see how much acetylene was made, right? Because the more of this, right, that could help us see. Okay? All right, so I'm going to do this in, where's my bottle here? All right, so I have a bottle here. I'm going to add 70 mils of water, which is like way more than 0.5 grams, so it should be plenty. Okay, I'll let it react for about 20-ish seconds to let the bubbles go, and then I'll ignite it. Now to trap our gas, I'm going to put a bandana on top of our bottle to keep our gas inside, because we don't want it just to leave, because then I can't explode it. Okay. All right, and then I have a little hole in the side of my bottle to ignite it with. Okay. Let me get my bandana fit here, because we want a snug fit. Some of it will escape through the hole, but it's small enough that we shouldn't lose all of it. Okay. I'm going to make sure we have a snug fit, because we don't want our gas escaping. Still a little loose. I don't know why it's not being the right dimensions I want. I will give you a countdown, 3, 2, 1, right before I light it, if you want to plug your ears.
Very loud.
Loud is relative. Tons, you know? Okay. Are we ready? I think so. Okay, so I have my rocks. Dump them in. Count to 20, and then we'll do it. Okay. Three, 2, 1. So yes, that was 0.5
That was 0.5.
grams. So what do we think? So if I do 5 grams,
It's gonna explode.
Can we do 5?
5 grams actually doesn't work. If I put it in there, it will bubble, but when I go to light it, it will not explode. Any ideas of why? True, Gavin. Okay, close your mouths here. Jack has a hypothesis. So good hypothesis, Jack says maybe there's not enough water. Not our problem, but not a bad thought, because that definitely would influence it. Have a smiley face for that. Levi?
The water, if they're not, like, is it not going to rip apart the water, and so there's not going to be enough, like, oxygen?
Ooh, what oxygen in what case? What do you mean?
So, like, when you're ripping apart the water, you're getting oxygen and you're getting nitrogen. But, like, if you're not ripping apart all of the water, then...
Oh, I see what you're saying. Not a bad thought. Have a smiley face. So the oxygen that we're using in this reaction is just what's already in the bottle from the air. So we're not creating that side of it. But not a bad thought. Have a smiley face. Porter?
Is it that the oxygen's not, like, concentrated enough in the air?
We flush it out, actually. It makes so much acetylene that all the oxygen gets pushed out the hole. And then there's no oxygen means no explosion. Now, There you go, Ian. So theoretically, if we had a bigger bottle, then you could get 5 grams.
Let's do it. It's got like a 5-gallon.
I don't.
That bottle.
And I don't know if I'm not using my water bottle. Have a smiley face, Ian, for that question though. But it's the idea once again of that stoichiometric ratio, right? Of if you get the best explosion is going to be a 2 to 5. That's going to be the loudest possible you can get is when you have a perfect 2 to 5 ratio. Having more of something only is going to be helpful as long as you have enough of the other thing as well. Okay? Questions on this? Okay, so homework tonight with this lesson is finishing up the back side of 4.1 and then 4.3. Okay, and then we'll continue with stoichiometry. So you don't need to start 4.5 yet. We'll do more with that next time. Okay? All right, let's look at our test.